Okay, let's look at the step response. And the step response, in that case, the input xt is going to be equal to the unit step, and in this case equal ut, and the Laplace transform of ut, which is the xs, would be equal 1 over s. So therefore, and as similar to the impulse response transform, we're going to use the gs instead of ys to denote the output transform or the response. And in this case, gs would be equal to, the gs is going to be equal to ts times 1 over s, because now xs is equal to 1 over s. And in this case, the inverse Laplace transform of the gs is just the inverse Laplace transform of the ts times 1 over s. Right? It's fairly straightforward, I would say. And let's look at the example of the step response. We have the circuit here. We have the input V1 connected to the non-inverting terminal of the op-amp, right? This is the op-amp operational amplifier. And we have the two resistances and also a capacitance in the circuit, and we are trying to find the voltage, the output or the response to an input of the step signal. So in this case, we recognize this is a non-inverting amplifier, and if we recognize this is Z1 and this is Z2, and the Vs, the transfer function, the voltage transfer function in this case is going to be equal V2s over V1s. That's equal to Z1 plus Z2s over Z1s. Right. I think last time we went through this in the little detail, right? And so in this case, we would have, we recognize Z1s is just equal 20k, which is 20,000, and Z2s is equal to the parallel of these two impedances. Let's use the 1 over the sum of the admittances. So I got a 1 over 10 to the power 4th, and plus the 1 over 10 to the power 7th over s, which is equal to 1 over 10 to the power 4th. So in this case, I multiply, let me do it in 2 steps. So 1 over 10 to the power 4th plus s over 10 to the power 7th. So in this case, I have, I multiply both the numerator and denominator by 10 to the power 7th. And times 10 to the power 7th, I got what I got here. I got a s, right? I get s in the numerator plus 1,000 on the numerator. I got 10 to the power 7th. So with that, I can get the voltage transfer function. So TVS, that's equal to 1 plus Z2, which is 10 to the power 7th over s plus 1,000 divided by Z1, which is 2 times 10 to the power 4th. So in this case, I got so 10 to the power 7th divided by 10 to the power 4th. That's the 1,000 divided by 2. I got a 500. So that's 1 plus 500 over s plus 1,000, right? Not 5,500. So this is TVS. So the GS would be equal to, TV times 1 over s, which is equal 1 over s plus 500 divided by s plus 1000 times s. And in this case, we need to do the partial fraction expansion of this on this term, on the second term, right? So let's call, I don't know, let's just call fs. So the fs is going to be equal to, based on the way we find the residues using the cover-up methods. Right? By the way, the cover-up method was first invented by Heaviside. So he was credited for this. He was a self-taught physicist. I got 1000 here, and so in this case, I get key 1 over s plus key 2 over s plus 1000, and the key 1 is just equal s times fs, and we evaluate this at s equal to 0 at this pole here, and in this case we got 500 divided by s plus 1000 because s being cancelled, so evaluate this at s equal to 0, that's 0.5. Based on some of the residues, key 2 should be equal to 0, or should be equal to -5, because key 1 plus key 2 should be equal to 0. And then let's see, keep an eye on that. If we made mistake, we will need to go back to find out. And in this case, we have s equal -1000. So we have 500 divided by s, we evaluate at s equal -1000, and without any surprise, that's equal to -0.5. So therefore, the GS is equal to 1 over s plus 0.5 over s, right? 0.5 over s plus -0.5 or minus 0.5 over s plus 1000. So in this case, or that's equal 1.5 over s minus 0.5 over s plus 1000. So the V2 in this case is just the inverse Laplace transform of the GS, which is, in this case, we have 1.5, right? 1.5 UT minus the second term here is based on using the S-domain translation property, and that should be E2 minus 1000 T and times the UT. And remember the time constant, that's the T over tau. So T over tau is equal, 1 over tau is equal to 1000. That means the time constant is 1 millisecond, right? So that's for the, this should have both. So this is the step response. Okay. I think I also have this example worked out in the Google Colab, and with the link with the Python code, but somehow the Python code has the difficulty of doing the inverse Laplace transform, although this is a very simple one. I had no idea why it happened. But in any case, so I write this after I did the partial fraction expansion. So this is the result of partial fraction expansion. I wrote this function. I did the inverse Laplace transform myself, and then I plotted this function and see how this what this look like. So this look like something like this. So I'm trying to plot a little bit to the negative side, just to see the step change here. So the voltage here on the output voltage V2 basically do a step change to 1 volt, and then gradually increase it to that's about 0.3, that's a half, 1.5 volts. So that's actually exactly what we are having here, right? So in this case, over time, then when time goes to infinity, the second term, the transient term, is going to disappear, and we're going to have the first term. So that's 1.5. So the steady state voltage should be 1.5. We're going to look at on the scope as well. Okay. So I see you in a moment as I set up the little experiment here.